Okay, hello everyone. In preparation for our class session on Monday, I would like to provide you with this finishing up of the filter section so that we don't get too far behind. So what we'll do in this video is there's probably going to be more than one part to it, but I'd like to go over the handout, which by the way I have revised to provide you with more information. So please do download and check out this new handout and follow along. And then I'll switch into OneNote to do an example problem. Okay, so on class, last time we had class, we discussed this terminology: ideal filters, non-ideal filters, linear phase, and what I've added is passive and active filters. And then this next paragraph, I'm not going to read the whole thing. I hope you do this before class, but this just discusses this is why we use active filters instead of passive filters. The picture here is actually from your electronics book, and so you can see again yet how these classes all interweave and relate. So this is an example of a two-pole, which means it's a second order low-pass filter. Okay, so this is a low-pass filter from your Neiman textbook. What we're not going to do in this class, we're not going to actually discuss how to design the circuits. We're going to look at the design of filters from the standpoint of the transfer function. So feel free then to explore this on your own. Okay, so the Butterworth filters, this is the magnitude of the frequency response. And the nice thing about this is where n is the order of the filter, then what happens is that no matter what the order of the filter is, and let me put another color here, the 3 dB frequency is the same. So depending on the order of the filter, the response will be steeper or shallower. But the frequency, the cutoff frequency, is the same for all stages of that filter, unlike what we explored before. So the Butterworth filter, a couple characteristics, so that it's maximally flat. That means in the pass band, it's flat, and then it decreases. So it's called monotonic or monotone characteristic. It doesn't fluctuate up and down. And when we actually form the Butterworth filter, we basically come up with 1 over a denominator. And the denominator is set by designing a denominator polynomial such that this condition is satisfied. Now, I'm not going to do these derivation of these polynomials, but you can find these tables just about in any kind of filter design handbook. So basically, you take the order of the filter you want, and here's the first 6, so let's not worry about anything above 6th order. And then you would just select that polynomial. So for example, if I wanted a 4th order filter, I would select this as my denominator and put that into the denominator of my transfer function. Now what this gives you, it gives you an nth order filter, in our case 4th order, low pass with omega c equal to 1 radian per second. And we'll talk about how we can choose other cutoff frequencies or get a bandpass filter or a high pass filter and so on. Okay, we're just going to get low pass of 1 radians per second. And then what we do is we implement these using cascaded op-amp stages. And that's why we leave them in these, we don't multiply out the polynomials. What we do is we take 2 second order sections and we cascade them. Okay, and so for 5th order section we would take 2 second order stages and a 1st order stage. Okay. Now on the Chebyshev filters, because we're a little bit behind, let's not worry about the design of these filters. Basically, I just want to contrast them to what happens with Butterworth, is that they actually give us a steeper transition region, but the trade-off is we have to have some ripple either in the pass band or in the stop band. Okay. So basically what that looks like, if you go to the figure that shows the comparison of the different filters, is we see a Butterworth filter. These are all the same order, so N is the same for all of these. You notice that the Butterworth is flat in both the pass band and the stop band. There are two types of Chebyshev filters. One has ripple in the pass band and it's flat in the stop band. And the type 2 is flat in the pass band and has ripple in the stop band. And there's yet a fourth type that is steeper yet, called the elliptic filter, and it has ripple in both the stop and the pass bands. So you see, it depends on what is most important to you. You can select the filter if you need a very sharp cutoff, but you're not too concerned about ripple on either pass band or stop band. You might want to go with the elliptic filter and not the Butterworth. If the flat pass band is important to you, then you'll want either a Butterworth or a type 2 Chebyshev. So frequency transformation, this is what I talked about before. How do you get high pass from a low pass characteristic? And so I'm going to ask you, if you haven't already, to stop this recording and read this section. And basically all we do is we make a substitution for S to do these. And I think if you just read through those and follow the next example, which will be in the next video clip, you'll be able to follow this. So again, stop this before you look at the example. Moving on to the rest of the handout, MATLAB has some very nice filter design tools that you should get familiar with. If you do a search in the MATLAB Help on Analog Filter Design, you should be able to pull up this document, which shows you, and especially if you're interested in the I've mentioned in this section, here's the Butterworth filter and the command that you need to get it. And this will give you the zeros, the poles, and the gain factor, which you can then transfer to a transfer function format. Okay, so this section on frequency transformation, this is what I referred to before. Remember, in the Butterworth filter, the polynomials only give you a low pass with omega c equal to 1 radian per second. So the problem with that is that we might want a high pass filter. We might want a band pass filter. We might want our critical frequencies to be something other than 1 radians per second. So this is the MATLAB way of converting. So you see here, from low pass, if we want to go from, if we want to set the frequency on a low pass filter, we just give the low pass filter we have, the numerator, denominator, and the desired omega c. And that will then give us another low pass with a different frequency. Low pass to high pass, same thing. Give the existing filter and then the desired cutoff frequency. To get a band pass, we give the center frequency and the bandwidth. And the same thing for band stop.